This week we're going to use MetPy's calculation functions to dispel a common urban myth. Welcome to another MetPy Monday. Hello, I'm John Lehman, a software engineer for Unidata. This week I wanted to address a common misconception that a lot of people have about the Coriolis force. And that is, of course, that it causes your toilet to flush in one direction in one hemisphere and the other in another. We know that this isn't the case as meteorologists, but we can actually use MetPy to prove it. I'm going to import metpy.calc as mpcalc. And from metpy.units, I'm going to import the units registry. Now, MetPy does have a Coriolis parameter calculation. And to do that calculation, we need a latitude. I'm going to say that our latitude is, let's say 35 degrees. That's a nice mid-latitude number. Now we need to calculate the Coriolis parameter. We can use mpcalc, Coriolis parameter. Using Shift-Tab to look at the docstring, we see it takes a latitude. And notice there's also a citation if you wanted to go look up this formula. And we can see that we get a number in per second, which makes sense for the Coriolis parameter. So how do we go about proving that the Coriolis force is not responsible for a toilet flushing? Well, the easiest way that I can think of is to use the conservation of angular momentum. So we're going to be looking at the formula of the radius times the velocity plus half of the Coriolis parameter times the radius squared is going to be a constant. So let's go ahead and code that up. And we're going to assume the radius of our toilet. We'll pick a very large number just for something nice. So let's say we've got a 1/2 meter toilet, so we'll divide that by 2 for radius and attach the unit of meter. And we'll assume that the velocity when we flush is 0. So 0 times units meter per second. So now let's calculate what our constant is for the conservation of angular momentum. It's going to be r times v, which we know is going to go away since velocity is 0, plus 0.5 times the Coriolis parameter times the radius squared. So there's our constant in meters squared per second. And we can rearrange that formula a little bit and calculate what would the velocity be after the radius has been reduced to, say, the drain diameter, which we can pick something relatively small, say on the order of an inch or a little bit larger, so 0.03 meters. I'm going to call that my radius 2. And that's divided by 2 to get our radius. So now let's calculate the velocity. Doing some basic algebra, it's going to be our constant minus 0.5 times f times r2 squared divided by r2. And if we look at v, we see that we get less than a millimeter per second. So if we calculate how long it would take the water to go in one complete circle, it's something on the order of minutes. So we can see that just by conservation of angular momentum and calculating the Coriolis parameter with MetPy, that the Coriolis force doesn't really influence such slow-moving, small-scale problems. But if you go through and replace these numbers with something on the scale of a hurricane, and wind velocities on the scale of a hurricane, you'll see that the number does become significant. This is one example of how you can use MetPy to do some quick back-of-the-envelope calculations to prove a concept to yourself or your students. I hope that you found this useful. We'll see you on next week's MetPy Monday.